we've been talking about hydrocarbons in chapter 10 and 11, and now we're going to introduce a third element, oxygen. You're going to find oxygen is pretty versatile on an organic molecule. It's going to give rise to 6 or 7 different classes of organic compounds, depending upon how the alcohol is on there. So, alcohols. Yeah, here we go. Here's our little guy. Looks like a little puppy dog, right? There's our oxygen. There's our OH group, a hydroxyl group attached to a carbon. And that is the functional group of alcohols, a hydroxyl group, an OH. So when you see these general formulas, ROH, they're saying R can be anything, and R could be a benzene ring. R could be 1 carbon, 2 carbons, 4 carbons, 12 carbons. It could be cyclohexane. So R is just a general term for some organic chain of some sort, and then you got the hydroxyl group on there. All right. In chapter 10, we said that alkanes and alkenes, alkynes, aromatics are all nonpolar. Well, now I'm going to get into some molecules that are polar. And why are they polar? Because this bond is polar. Oxygen-hydrogen bond. In 1305, hopefully your instructor got through to you on the fact that water is a polar molecule. And it's polar because oxygen has a high electronegativity, oxygen has a high electronegativity, hydrogen has a low electronegativity. Although they're sharing electrons, the electrons favor being around the oxygen, and electrons are negative. And the proton out here, without an electron around a hydrogen, you have a proton. And the electron is there sometime, but most of the time it's up here. This ends up to be positive end of the molecule, or the bond, positive, negative end of that bond. Polar, it's a polar bond. It's not so with these other bonds here. They're non-polar bonds, and the rest of the molecule is non-polar, but right here is polar. So it can hydrogen bond. And so let's see here. Imagine a line right there. This is one container over here, and we got another container over here. What's in this container? An alcohol, pure alcohol. There's your, whatever it is, 1 carbon or 5 or 8, whatever, and there's your OH bond. Here's another OH bond. The hydrogen here, which is positive, is attracted to the oxygen over there, which is negative. That's a hydrogen bond. And it's coming about because of the polar nature of this bond. This hydrogen is attracted to another oxygen over there. So the alcohol molecules themselves are attracted to each other through hydrogen bonding. And then if we put some water in here, if you threw some water into the alcohol, you would find out that the water will hydrogen bond with the alcohol. Again, the same way. Hydrogen is attracted to an oxygen. Oxygen of the water is attracted to the hydrogen on an alcohol. With me? This is why a polar compound will dissolve in a polar solvent. The polar solvent is acting like the molecule itself. It has an attraction for the other molecules. So these bonds here are within a molecule. These bonds here are between molecules. Hydrogen bonding. They're not real strong. They're not as strong as these covalent bonds, but they are important. They drive solubilities, they drive boiling points. All right, so very first thing to know about alcohols is that they are polar. Okay, now compare this. We've got an alkane right here. To this, we have an alcohol. I'm skipping the one in between. We haven't even introduced these yet. But look at the difference. There's propane. Propane, it boils at minus 42 degrees centigrade. Here's ethanol. Now, I don't have 3 carbons here, but I'm replacing a carbon with an oxygen. I have about the same molecular weight. And this thing boils at almost 80 degrees centigrade. Minus 40 up to 80, 120 degrees higher boiling point. Why? Because of the attraction the molecules have for each other. They're attracted to each other. In order to get ethanol to boil, you have to break it away from the other ethanol molecules. And that takes energy. You got to heat it up, get enough energy in there that those hydrogen bonds, those molecules start getting excited, and bam, the hydrogen bond breaks and it evaporates. It boils, goes into the vapor phase. So look at that, 120 degree difference in boiling point. This is the effect of hydrogen bonding. Okay, now solubility. There's ethanol again. Here's butanol. Butanol. Okay, you're already hearing me use some of the names here. Ethanol is completely miscible in water. You could put 90 grams of ethanol together with 10 grams of water and it'd be soluble in each other. You could put 10 grams of ethanol in 90 grams of water, be soluble. But this one here has 1, 2, 3, 4 carbons and an OH, and the solubility starts dropping off. Let's look at a graph of this. Okay, what's going on here? Okay, when you look at a graph, sometimes I go too fast. You have to get your feet on the ground. What are we graphing? Along here, we're looking at number of carbon atoms in the molecule. 1, so that would be methane, and way up there would be methanol, because this line here is alkanes. And alkane solubility, they're all nonpolar, they're not very soluble in water. This graph here, or the y-axis, is solubility. Grams of this compound per 100 milliliters of water. So there's 1 gram. This is like 0.2 grams. Alkanes are very insoluble, a little bit. So don't think if you see gasoline on top of water, you can just kind of decant off the gasoline and drink it. There's going to be a little gasoline in the water. 0.2 of a gram. This is gasoline, 8 carbons long. 0.2 of a gram per 100 grams of water. Okay, but here's the alcohols here. 1, it's off the charts. 2, off the charts. This is ethanol, propanol, butanol. About 8 grams per 100 milliliters of water. Pentanol, 5 carbons long, 1 OH group. Let's look at pentanol. There we go. Just 3 more carbons. So here's pentanol. We're starting to get it a little bit longer. I need 1 more hydrogen there. But we got an OH over here, and then we're starting to get this long chain. And what's happening? The solubility is dropping. as the chain length increases, the solubility in water is decreasing. Why? The only part of this molecule that is polar is that OH group. And if we ignored that, that looks a lot like an alkane, doesn't it? Which are nonpolar and not soluble in water. So the longer we make this molecule, the more it starts acting like an alkane. And when it finally gets 7 carbons long, even though it is polar, it has some polarity to it, it's indistinguishable from an alkane in terms of solubility in water. You with me? That's what we're doing here. We got a part of the molecule that is nonpolar and one little group over here that is polar.
Is it because it's getting harder to hold on to because it's getting too big?
Well, the only thing that water is attracted to is this thing right here. So if you had a water molecule, the hydrogen would hydrogen bond to this, but it's not, the water doesn't like this part of the molecule.
Yeah, attach that one. So.
Yeah, it doesn't have an affinity for this nonpolar part of the molecule. So eventually there's so little attraction that this floats to the top and is no longer soluble in the water. Now, in the homework, you're going to have to understand one other thing. So there's our, let's look at right here. We got 1, 2, 3, 4 carbons and an OH, 7 grams per 100 milliliters. 1, 2, 3, 4 carbons. We have 2 OHs. Why I don't just leave these over here. We've got 2 OHs. And what does it say? It's very soluble. This is just as soluble as that. At 4 carbons. But it's got 2 OH groups. All right? All of a sudden now there's water that likes to be around here, there's water that likes to be around this end of the molecule, and this little thing kind of gets lost in the middle. Yeah, it's nonpolar, but there are now 2 OHs per 4 carbons, which is the same as having 1 OH per 2 carbons. This is completely soluble in water. This is completely soluble in water. Well, you put the 2 together and it's still very soluble in water. So chain length matters. The longer the chain length, the more nonpolar it is, but the number of OH groups that are on it matters. The more OH groups, the more polar the molecule is. All right? So just kind of understand that. Nomenclature. Okay, let's get into how do we name alcohols. Simplest alcohols go by common names: methyl alcohol, ethyl alcohol, propyl. The IUPAC name is to take, so that's a common name, methyl alcohol. The IUPAC name is to take methane and drop the E and add OL. Where are we getting the OL? We're getting the OL right here from the word alcohol. All right, so we're going to attach that OL on the end, and it's going to be cluing us in that we're now talking about not an alkane or an alkene, it's an alcohol. And then we need to, so methanol, ethanol, propanol, we should start using numbers to show where is that OH group. All right, here's an example. So again, rule number 1 is find the longest chain. Okay, choir? That's what you're supposed to say. Say rule number 1. Find the longest chain. Doesn't matter that we're now talking about alcohols. That's still the starting point. 1, 2, 3, 4 carbons. And then start from the end closest to the OH. Why? We're going to put OL at the end of this thing. We're calling it butanol. So we want to get to that OH as soon as possible. So we're going to start counting here. 1, 2, not here. 1, 2. So 1, 2, it's 2-butanol, and it's 3-methyl-2-butanol. Naming cyclical alcohols. So if I just had an OH group on a 6-membered ring, it'd be cyclohexanol. Oh, I don't want that. So that's just cyclohexanol. I'm just using the rules we just went over. Its name without the OH there is cyclohexane, so we drop the E and we add OL. We got cyclohexanol. And now there, we put a methyl group up there. It's 3-methyl cyclohexanol. And I don't need to put a 1 if this was not cyclical, if it was hexanol, then I would need a number. But on cyclohexanol, wherever the OH is carbon number 1. It's on carbon number 1. And we're going to count from there. So the 1 is unnecessary. Okay? Yes?
What if you have 2?
If you have 2 OHs, then it's diol, and you would need numbers. If you had 2 OHs, for example, well, let's do a simpler one. Let's do just, there's 5. You could have 2. And it would be a diol. This would be pentane. So it'd be pentanol, pentane diol, I guess. Is that what it would be? Ethylene, glycol, diol. I think I have some diols up there, but then we would need numbers. So this would be 2, 3. It might be pentadiol. I'm not sure if we put that N in there or not. Pentane diol. So see, there's your di. You can have a triol. Let's see if we get an example of that.
After the name is the
Oh yeah. Here's 1, 2, 3 propane triol. So that might be pentane diol. Pentane diol. Would leave the E in there. That's what we do. Okay. Sorry about that. I had to go back and see. So we would leave the E because we don't want an N and a D right next to each other. That's the only reason. Just better English. We would call it pentane diol. All right, so we're not going to drop the E because you can't, it's hard to pronounce an ND.
Why does it go after on this one? Before we were playing before, now it's after.
The di? Well, we didn't, remember hexadiene? Hexadiene? When there's 2 double bonds? What do you mean after? The D, the di?
Yeah, weren't we putting them before?
Well, when it was like dimethyl, yes. But when it's actually in the parent name,
Okay.
you put it right in front of the OL, which is the OHs. Okay, here you need 3x5 cards for these. Remember, we learned in chapter 10 we learned this substituent, which is a tertiary butyl substituent. Tertiary butyl substituent. Well, if here where it would attach to an organic compound, I put an OH in there, I now have tertiary butyl alcohol. That's tertiary butyl alcohol. And now you can see the other one on the right is an isopropyl group with an OH on it. It's isopropyl alcohol. It's a very common alcohol. That's rubbing alcohol. All right, now what are the IUPAC names of those two molecules?
Isopropyl is 2-propanol.
Yes, that's right. 2-propanol.
And T-butyl alcohol is 2-methyl-2-propanol.
2-methyl-2-propanol. Everybody see that? Am I going too fast? Yes? Yeah? 2-methyl-2-propanol. Anybody have any question about those being the IUPAC names? So there is a 1-propanol. And there is a 2-propanol. Okay, 1-propanol has the OH on the end. 2-propanol has the OH in the middle. You're going to find out in this chapter how critical that is, because these two alcohols react differently. 1-propanol and 2-propanol react differently. They undergo different reactions, produce different products. So this is 1-propanol. If I were just, I would call this propyl alcohol or normal propyl alcohol. I would not call this one propyl alcohol. This is isopropyl alcohol, okay? So in terms of common names, you need to, propyl alcohol is referring to 1-propanol. Isopropyl alcohol is referring to 2-propanol. Can I move on now? Just real quickly, medically important alcohols. Methanol is used as a solvent. It's toxic. It can cause blindness. Can be used as a fuel. You go into a restaurant, you have these little things sitting there burning. There's methanol, where you can see a little glass container with a liquid in there and a wick coming out of it. The liquid in there is methanol. It burns, and it burns with a really nice clean flame. Ethanol is the alcohol that's in alcoholic beverages. All right, so alcohol is not a specific term, it's a general class of organic compounds. Alcoholic beverages have the particular alcohol, ethanol. Isopropyl alcohol or secondary propanol or 2-propanol is an industrial solvent, a disinfectant. Okay, ethane diol, 1,2-ethane diol, or ethylene glycol. That's the major component in antifreeze. It's what's in your radiator. About 50% is ethylene glycol and 50% water. It's a mixture of this antifreeze and water. Extremely poisonous. Yeah. And people have been poisoned by this, either inadvertently or in some cases, people have used this in certain things that you would ingest, like cough syrup. It's happened in many, many different countries, usually at different times. It probably happened in this country 30 or 40 years ago. It's happened in other countries as recently as 5 years ago, 5, 6 years ago. It's cheap, it tastes good, and it can kill you. Now, why would you put that in cough syrup? Because it's cheap. Criminal. But it's happened. It's happened inadvertently, but it's also happened by design. This molecule here will be an important one, glycerol, in Chapter 17. You don't have to worry too much about it right now. In Chapter 17, I'll have you learn that molecule. Glycerol, or 1,2,3-propane triol. It's got an OH on every carbon. This is not toxic. Your body, this is the backbone of triglycerides. This is where triglycerides get their name from glycerol. Glycerides contain glycerol as a backbone molecule. But we'll learn that in Chapter 17. Okay, classification. Let's go through the classification of alcohols, and then hopefully there'll be a little exercise I can give you, and we'll take another little break. Primary, secondary, and tertiary alcohols. All right? Primary, secondary, and tertiary. What are we talking about? Here are some examples. Methanol is in a class all by itself. So it's not primary, secondary, tertiary, it's just methanol. Ethanol. Ethanol is a primary alcohol. What do we mean by that? The OH is attached to a carbon that is only attached to one other carbon. One. It's a primary alcohol. 2-propanol, or isopropanol, isopropyl alcohol. The OH is attached to a carbon, but that carbon is attached to two carbons. It's a secondary alcohol. And this one, the OH is attached to a carbon, but that's attached to 1, 2, 3 carbons. It's a tertiary alcohol. All right, that's how we classify. So this, just to be clear, this is isopropanol, or isopropyl alcohol. This one, 2-methyl-2-propanol, what is that also? What's its common name?
T-butyl alcohol.
T-butyl alcohol. This one's kind of given the answers, but let's look at A, B, C, and D. A is what kind of an alcohol? It's a secondary alcohol. B. tertiary? Yeah, B is a tertiary alcohol. It's attached, it's attached to 3 carbons. C, primary. Okay, now D is it's at cyclobutanol. That's cyclobutanol. What kind of an alcohol is that? Matt? Secondary. This carbon is attached to 2 carbons. So that's a secondary alcohol. So if we had over here cyclohexanol, if I'd be looking at that, this carbon here is attached to 2 carbons. So a cyclical alcohol like that, what you have to do is actually look at it and say how many, let me give you say, oh, we tricked you. Well, let me trick you right now. Let me trick you when it doesn't count. All right? All right, so let's draw and then determine what kind of alcohol So draw 1-methyl cyclohexanol. Draw that molecule and then tell me what class of alcohol it belongs to. This is a hard one. Where is the methyl group? It's where? Carbon number 1. That puts it on the same carbon as the OH group, right? So what class does that fall into? Tertiary. Tertiary. That's a tertiary alcohol. Look at here. Here's your carbon. This is the carbon the OH is attached to. And there's 1, 2, 3 carbons attached to it. So this is a tertiary alcohol. So I can't give you a hard and fast rule. Basically what you got to do is look at this OH group, look at the carbon it's attached to, and then ask yourself how many carbons is that attached to. And that'll tell you whether it's primary, secondary, or tertiary. Okay, let's take another break until 1:30. I'll leave that up right there. Try to name those alcohols. Name all of those alcohols. I'll do this one right here. The bottom one, we saw those. And this is glycerol. This is on an earlier slide. It was 1, 2, 3 propane triol. You name the other 3.